Okay, we're going to start our last chapter, Rigid Body Momentum. It's chapter 19 in your text. And so I want you to recall traditional momentum for particles, which we've seen before. And so what we did is we took Newton's law, integrated it, and that brought out the following equation. So we said mv1 was a linear momentum term, and this integral of the force was called impulse, leading to mv2. Going to rigid bodies, this just adjusts in a very logical way. So we simply now have mass times v1 of the center of mass, and then we have linear impulse in the usual way, leads to the momentum associated with the velocity of the center of mass in state 2. Okay? If you have multiple masses, you would have an mv1g, mv2g. You're going to have one of these terms for every mass. But you're looking at the center of gravity of the mass. Likewise here. Okay? So the problem comes down to how we deal with rotation. Now, when we did Newton's law, so all this comes from Newton's law. So Newton's law is actually, with rigid bodies, sum of the external forces equals mass times the acceleration of the center of gravity. All right. So when we did our chapter 17 Newton's law, we came up with the following equation. The sum of the moments about some point O, where O is arbitrary, is Ig alpha plus R from O to G, so this other point we want to do, cross mass times the acceleration of the center of gravity. All right? And again, we have one of these terms for every mass that we have. All right? So relative to rigid body momentum, the idea is the same. We're going to integrate this, integrate that, and see what happens. All right? Integrating over time, this just leads to the following term. Now note up here, we called that linear impulse. So guess what we're going to call this one now, because there's rotation? Angular impulse. All right? So one of the clues we said was to know when you had momentum is there were 3 clues. That impacts occur, and as we go to rigid body, same story. If you see the statement regarding impulse, this or that, that's an instant clue. This is a momentum problem. And then the last thing is if there's some discussion of velocity relative to time. Okay, because we're integrating with respect to time, so time and velocity tend to be related. All right, so here's this side of the equation. We go to integrate it. So when you integrate, Ig would be constant. When you integrate alpha, you get omega. R is constant, M is constant. Integrate acceleration, you get velocity. So, taking that down, we come up with the following. Now, so we have these terms. So for every mass, we're going to have these terms. So look what we have. When you integrate it, you get an H2, so that there'll be a state 2 and a state 1. So on each side of the equation, we're going to have one of these for every mass. And so what is the nature of the momentum term? Instead of mv1, now we have Ig omega plus R from the O that we care about to G cross mass times the velocity at the center of mass. This is state 2, that being state 1. Okay, so this is now our this is angular momentum. So up here, that's momentum. The H is angular momentum, and this is angular impulse. All right? So, if looking at this new equation we have, if the mass is purely rotating about the center of gravity, well, that means Vg is 0. So we're left with the angular momentum is simply Ig omega. So that looks a lot like what we have for linear momentum, as these terms disappear. All right. If the mass is not rotating, this is a huge point right here. So suppose we have a mass hanging from a pulley, a spool, which is now letting down rope as this thing falls. All right. When we go to analyze this whole system, because part of it's rotating, this mass still has angular momentum. Relative to O, we can still consider angular momentum. So look at this mass. Is it rotating in and of itself? No, it has no angular velocity. So this Im, as I'm calling it, times omega m, that's 0. But relative to this point of rotation, I can still go r from O to m cross the velocity of the center of mass at m. So if a mass is not rotating, it still has angular momentum. Why do I care about this? Okay, things that are going in a line can still have angular momentum. But things that are rotating, there's nothing we can do to give it linear momentum. It doesn't have it. So to analyze a big rotational system where some of the parts, like this thing falling down here, are just purely translating, we cannot use linear momentum to solve this problem at all. We have to treat the whole thing using angular momentum, because the stuff that's linear can be related to the point of rotation via this equation. We must treat everything as angular momentum. All right, that is sort of the freaky thing for people, is I know this is translating, but it still has angular momentum relative to this point where rotation takes place. That is the point that can cause people a lot of confusion until you just let it go. We derived what this looks like up here. Every mass, whether it's rotating or whether it's just translating or a combination, has one of these terms. Okay, so you just have to go with it. All right. Now continuing. So far, here's what we have. Bring that down in. Here we go. So we have, just like we had with linear momentum, we have h1 plus angular impulse gives us our second state of angular momentum. All right, where h is about some point O. So here's the momentum. So h is ig, in this case, say omega 1 or omega 2, r from O to g, cross the mass of the velocity of the center of mass, and it can be state 1 or state 2. All right, O is not a number, it's just the point at which we're taking our moments. Okay, fine. So let's, just to see what else we can do with these equations, I want to consider a disk that's in pure rotation, but it's pinned off the center of mass. So we're going to consider the following. All right, so here's a disk. Here's the obvious center of mass. It's pinned here, and it's got omega. What can we do? Okay, so I'm going to take angular momentum about O, that's the point of rotation, and it would be ig omega plus r from O to g cross mass times velocity of g. Fine. Now I'll note Vg, because it's rotating about O, is nothing more than omega cross r from O to g. If we do this cross product, I'll let you do this in yourself. Do omega cross r, find where the v is, and then do an r across that v. Here's what you're going to come up with. You'll have the ig omega comes down plus m r og squared. This is just a magnitude in the omega direction. Whichever omega direction whatever direction omega was going in, this result will be going in that direction. All right. Now, suppose I factor out the omega. I had to have ig plus m r from O to g squared, like here. Well, this is just the parallel axis theorem. So what do we have here? This is just mass moment of inertia at O. So if I have a body with pure rotation about an O not equal to g, I can express angular momentum as IO times omega. All right? So this is just a special case for pure rotation away from the center of gravity. So it's time to summarize what we have. For pure translation, we have traditional momentum. And that means that we have, for pure translation, omega 0, so hg would be 0. So this is where we're taking this at g. However, we can be in pure translation relative to a spot that's not the center of gravity of the mass. This may not be 0. The angular momentum tend to be non-zero, which may be useful solving a problem. For pure rotation about g, so that's all we have. The linear momentum is 0 because velocity of g is 0, and we just have angular momentum is ig omega. And for general motion, we have the following. So these are the general equations we have: linear momentum, angular momentum, and this is what in general, this is about g, and about another point, O, we get the following. Time to start doing some problems. We'll get at it in just a moment.